Hi, my name is Yasanayake and I work for Maricopa County Department of Transportation in Phoenix, Arizona as a senior geotechnical and pavement design engineer. Maricopa County Department of Transportation is abbreviated as MCDOT, MCDOT. My topic is mechanistic empirical pavement design in Arizona in the United States. ME design was available in the United States since the mid-2000s. However, MCDOT has been using 1993 AASHTO design method until 2018. AASHTO stands for American Association of State Highway and Transportation Officials. This presentation compares the two pavement design methods and how MCDOT is going forward with flexible pavement design. Arizona State and Maricopa County are shown in Figure 1 and Figure 2 respectively. 1993 AASHTO pavement design. In this method, traffic loads and subgrade support are the main inputs. Climate for a geographical location is summed up with a seasonal variation factor. In 1993 method, traffic load is estimated based on equivalent single axle loads or easels for short. One easel corresponds to 18,000 pounds. Federal Highway Administration, FHWA, classifies vehicles into 13 classes. Pavement design considers only classes 4 through 13. Typical design period for flexible pavements is 20 years. A typical pavement structure is shown on the sheet. The resilient modulus of subgrade soil quantifies the support provided by the subgrade. R value test is correlated to resilient modulus. MCDOT's roadway design manual shown in Figure 6 gives the procedures. R value stabilometer is shown on the next sheet. And climatic conditions are taken into consideration by using a factor called seasonal variation factor, as mentioned before. The pavement design guide published by Arizona Department of Transportation, ADOT, provides a map of the state with contours of seasonal variation factors. The factor for Maricopa County is 1.0. Once the traffic, subgrade, and climate data are available, an empirical equation is used to obtain a value called structural number. Then layer thicknesses are computed to satisfy the required structural number. The pavement structure typically contains multiple asphalt bound layers and unbound layers, such as aggregate base constructed on prepared subgrade, as shown in Figure 9. DARWin program is used to do the thickness design. In this method, performance of the design pavement is assumed, but there's no way to predict the performance. Since the 1993 method is based on very limited research, there's a possibility the design can be either over-designed or under-designed. Now let's move on to ME design. MCDOT started using ME design since 2019 in parallel with the 1993 method. Unlike 1993 method, ME design is based on decades of research, mechanistic behavior of the pavement structure, and on performance criteria. National performance criteria is shown in Table 1. For example, the International Roughness Index, IRI, value is set to 172. And when IRI exceeds 172, the pavement is considered failed. In ME design, climate, traffic, and material data are handled differently than 1993 method. 3 hierarchical levels, level 1, level 2, and level 3 are available. Level 1 represents the most advanced level while level 3 represents the lowest level. Level 2 can be used when some intermediate test data are available. Now going to ME design traffic. In ME design traffic, it is not just ADT. Many traffic parameters such as average annual daily truck traffic, AADTT, axle configuration, vehicle class distribution, etc. are entered. Up to 20 years of historic climatic data is provided with the program, such as daily fluctuation of ambient temperature. ME design allows the user to select a climate location. The depth to groundwater is also entered under climate data. Now let's look at mechanistic principle. Mechanistic principle adopted in ME design assumes that the pavement can be modeled as a multi-layered elastic structure system. The relationship between pavement deflection and compressive and tangential strains is modeled. The damage caused by the applied loads over the design period is quantified mechanistically. And then the damage is correlated to various distress types empirically. Therefore, the design method is called mechanistic and empirical. The amount and nature of material properties used in ME design are dependent on the hierarchical level. The most important properties include binder viscosity and dynamic modulus of the mixes, that's called E star. The temperature viscosity relationship is obtained by performing 3 different tests on binder, namely softening point, Brookfield viscosity, and penetration test. Then dynamic modulus, E star, of the mix is determined for several load frequencies applied to the asphalt concrete specimen at different temperatures in the lab. Figure 19 shows how E star is computed from the test data. Then table 2 shows E star values of a mix obtained after conducting 30 tests. The time temperature superposition is used to obtain a single curve called master curve for a mix, keeping the 70°F curve as reference. The other 4 curve segments are shifted. Shift function is required to shift the values back to the original position. Figures 21A and 21B show master curve and shift factor function respectively. Properties of unbound layers are also entered into the program. Figure 22 shows the tests. Local calibration. MCDOT performed local calibration using 15 roadway projects. The measured data were compared to predicted data and observed bias was eliminated by adjusting selected calibration factors. Figure 23 shows MCDOT calibration factors along with ADOT and national factors. Running the program. The program takes less than 10 minutes to complete the 5-step process. It generates an output report, including a summary sheet, input data, material curves, and performance of pavement over the design period. The first page of output gives the predicted performance. See the highlighted column in figure 5. If there are failed distresses, the program should be rerun with revised pavement structures until the output has no failed distresses. In conclusion, it is obvious that the ME design is superior to the 1993 AASHTO method because it is based on extensive testing and research conducted in various climatic conditions. It uses a mechanistic approach along with empirical correlations. and the program can be calibrated to local conditions by the user if necessary. However, there are challenges. To use level 1, expensive testing is required. The design process is not that simple compared to the 1993 method. The ME design software is expensive to maintain as annual cost runs over $7,000. And users should gain good knowledge and experience to input meaningful data, interpret analysis, and make reasonable decisions. To overcome these challenges, MCDOT's strategy is to provide training for the consultants if needed and share the use of software program. Thank you.